So what is reflection? So reflection is, so we are barely talking about reflection of light. Okay. So reflection is when a light ray goes and hits a surface between two mediums. For example, let's say this is air and let's say this is glass. So it hits this surface between the mediums and then it reflects back to the same medium. So if you look at both these rays, you can see both these rays are in the same medium. This rays is incident rays in air and also the reflected rays also in air. So both of them are in the same medium. So that is called reflection, bouncing back to the same medium. And for light, it is very interesting because the angle of incidence is equal to the angle of reflection. So theta I is equal to theta R. So the other important thing is how do we measure this angle? So this angle is the angle between the ray. So this is the ray, right? Incident ray and the normal that you draw to this surface at the location it bounces off. So at the location the ray hits the surface, you draw a normal. Normal means a perpendicular line. And the angle, incident angle, is the angle between that normal line and your ray. Okay, so it is not this angle. So a lot of people I have seen, they write this angle. So it is not this, okay? It is this. So that is the law of reflection, which is very easy. And this law is true for any reflection. What do I mean by any reflection? So reflection through a rough surface. So it is true for a reflection through a rough surface, smooth surface, or even it is true for reflection by plane mirrors. Even it is true for spherical mirrors. So it is true for any ray of light reflecting. Okay. So the first type of mirror, the first type of thing that we are going to learn under reflection is a plane mirror. So you all know about plane mirrors because that is the mirror that we are seeing in our day-to-day lives. Okay, so in a plane mirror, what is happening? So if you stand in front of a mirror, or if there is an object in front of a mirror, what you see is an image. So this is your image that you are going to see, and it is inside the mirror, right? So can you touch this virtual image? So I will explain what virtual really means. So can you touch the image found by a mirror? No, right? Because it is inside, it is not real. So I will give you the correct definition of virtual in a few seconds. So the important thing is this is inside the mirror. In other words, this is the most important word. It is behind the mirror. The image is behind the mirror. It is not in front of the mirror, right? It is behind the mirror. And what else can you say? So we figured out it is behind the mirror. What else can you tell about the object? Is it upright? Yes, right. It is upright. It is not upside down, right? When you look at your face in the mirror, you don't see you standing upside down. So it is upright. What about the size? Same size, right? So if you look at yourself in the mirror, you see the same size. You don't see a tiny face or a huge face. So it's the same size. What else? So the other important thing is it is flipped. So if you raise your right hand and if you look at the mirror, the person in the mirror is really lifting the left hand. So it is flipped. Okay. So this point right here, first point I wrote, behind the mirror. So behind the mirror means our image is formed behind the mirror. But we know through a mirror, light rays cannot go inside, right? Light rays cannot go inside the mirror. So what we really see is something not real. These light rays which are coming towards our eye from this object looks like these rays are coming from it, but these rays are not really coming from it, right? It looks like it's coming from it. So virtual is when it seems like the light rays the reflected light rays are coming from the object, are coming from the image. But for real, it is not the case, right? For real, these light rays are not intersected here, or they are not really converging at this point and coming towards you. That is why it is called a virtual image. If it was a real image, then light rays, so you will see real images in few slides, light rays actually intersect and come towards your eye. So if it was a real image, these light rays will be converged here for real. They will intersect here for real. You don't have to like draw dotted lines to show this. Okay, so it is a real image if light rays actually converge or intersect at the location of your image. It is virtual if it looks like that, but light rays really do not do that. Okay. Okay, so we are okay with this. So this word behind the mirror is important because when we go to the next type of mirrors, you will see that we need it. Behind the mirror, in front of the mirror, those words are important. So a plane mirror forms an image that is always virtual and upright. We know it, right? Because the image is formed behind the mirror, right? Plane mirrors produce images, see, same size. See, is it possible to see a virtual image? Yes, right? You can see yourself in the mirror. That means you can see virtual images. So the answers should have yes, and let's see which one is the correct one. The rays that appear to emanate from a virtual image can be focused on the retina just like those from an illuminated object. That is true, right? So rays that appear to come from these virtual images. So that is what's happening, right? So the rays, although they are not really coming from the image, they appear to come from the image, and they can still be focused in our eye. So I think the answer is C, and the answer D. It looks correct. Whatever they are saying is correct, but it is not really explaining the problem, the question. So they're asking about virtual images. So in D, they are saying everything we see is virtual. It is not true, right? So for example, let's consider the pencil or the pen that you are writing. So we know it is not giving out light, but light rays which fall on it will come to your eyes, and that is how you see it. So this is a real object, right? The pen or the pencil that you are writing with is a real object. So here they are saying everything we see is virtual because most things do not themselves give off light. but only reflects light. So this part is correct. So everything will not give off light, but they will reflect light. But it is not because they are virtual. These are real stuff. This is a real object which gives off light due to reflection. The light rays actually came from this, right? It actually reflected off this. So that is why it is real. So D is wrong. So answer is C, okay? So D and C are a little bit confusing. I think for the answers, I put D. Okay, so make sure you correct it. My answers that I will upload will be wrong. This one it will be wrong. Okay. So quickly do this and make sure you read whatever they're asking correctly. Check which angle they're asking. 15. So if I draw the ray diagram from this surface, it will reflect. And again from this surface, it will reflect, right? That is what is happening. Okay. So if this is 15, what can you tell about this angle? This is 75, right? Because 15 plus 75 is 90. This is the normal. And we know according to the law of reflection, if this is 75, this should also be 75. Okay. Now the problem is figuring out this angle. So how to find it out? So if I extend this, I can complete this triangle, right? So if this is 75, this is 90, what should be this angle? It is 15, right? Because this is 90 plus 75 plus this angle. If I write it as theta, it should give you 180 angles of a triangle. So from this, you can get theta as 15. So this angle is 15. Therefore, again, law of reflection. If this is 15, this is also 15. But now we have completed this. Now let's see what they're asking. They want us to find the angle the outgoing beam will make with the second mirror. So they want this angle, right? They want us to find this angle. So what is this angle? This is 90, right? So if this is 90 and this is 15, this angle is 90 minus 15, which is 75. Okay, so in these problems, make sure you read the questions very carefully. So there are few things that you have to remember in this part, starting from these words. Okay. So spherical mirrors, from the name, we can kind of figure it out that they're talking about spheres. So these mirrors, you can think of them as you can think that these mirrors are made up of spherical surfaces. You can think that they are made up of glass balls like this, glass spheres. So this shape is called a convex mirror. And how do they make it? They take a circular or a spherical shell of glass, and then they cut this piece out. Okay, then they cut this out and darken this surface, darken the inside surface. Then you get a mirror like this, right? Curved in this side and darkened in this side. Okay, so I want you to look at this, compare this convex mirror with the circular diagram and tell me where the center is. So if I mark this, where will be your center of this mirror? Is it towards your right or left? What is it? Right or left? Here or here? Right? So here. So your center for this convex mirror is behind the mirror. Can you see it? So light rays are coming this way. That means this is your behind the mirror. So your center is behind the mirror for the convex mirror. Okay. So the other type of mirror is a concave mirror. So in that also we do the same thing. We take a circular glass ball, cut a piece, but now we color the outside. And your mirror surface has this cave shape. It's like a cave. So we call it a concave mirror. Okay. So can you look at this and tell me where your center is? Left or right? Compare this with this. Left, right? Yes. So this is your center. It is in front of the mirror, right? Can you see it? It is in front of the mirror. So this behind and in front are very important when we go to the next part. And the other thing is you have to remember these names. So when light rays fall on this convex mirror, what happens is they tend to diverge or tend to go away like this. Still they follow the law of reflection, but due to this surface, shape of the surface, these light rays tend to diverge from the surface, go away from the surface. See? Therefore, we call it a diverging mirror. So whenever you see diverging mirror, what they mean is convex mirror. Whenever you see converging mirror, that means a concave mirror. So this converging, diverging thing, this is valid for a mirror. You will see when we go to lenses, this is completely opposite. Okay, so it will be good if you can kind of like after today's discussion make a like a short note like thing having all the things that you learn for a mirror separately. Okay, because lenses are very similar to this but completely opposite. So you might get confused if you get a lot of information in the same day. Okay. Okay. So before we go deep into this, I want you to know a few definitions. So you all know the center, right? So here I have drawn these two diagrams in the opposite. Opposite means in the previous slide we did convex first, right? Here I have written concave first and convex second. In the concave, this is the center. It's correct, right? This is the center. If you complete the circle, this is the center. And the midpoint between the center of the sphere, or this is called the center of the curvature. Of this whole curvature, this is the center, right? And this P point is the center of the lens. So your lens is only this part from here to here. So this is the center of the lens. So these letters are very important because in problems, they will just use C, F and P. And the point in the middle between your center and the P point is called the focal point or the focus. So it's called the focal point or the focus of your lens. Okay, so this is right in the center. So if so, I'll call this distance. Since this is the center, this is the radius, right? Radius of the curvature. Since this is the center, I can call this length the radius. And F here, I said it is right in the middle, right? So F is the distance to F is R divided by 2. So this distance is R divided by 2. Okay, so always in these problems, we start measuring distances from this P point. Okay, we start measuring distances from this P. So from P to center, the distance is radius. From P to focal point, the distance is simple F, focal length, which is R over 2. Okay, so are you okay with these few letters? C, F, P, and capital R and simple F. Simple F is the distance between P and the focal point. Okay. Okay. And this line right here. So this is the line joining your P point and the C point. So this line here is called the principal axis. So they are just names. The principal axis. I don't know whether the principal letters are correct. I don't know. So principal axis. Okay. This line is called the principal axis. So are you okay with the names that we call each of these things? Okay. So if you are okay with this, you can see that these letters are common to any type of mirror. So here, for this one, C is here, P is here, this is the principal axis, and this F is, this is the radius, right? So this distance is simple F, which is capital R over 2. So those letters are like universal to any mirror. Okay. So before we go forward, we need to learn 3 types of rays, light rays, 3 types of rules for drawing light rays, because it becomes very useful when we are going to draw ray diagrams. So the first one, any ray which goes parallel to the principal axis. So you know what principal axis is, right? So any ray which is parallel to the principal axis will go through the focal point, or will go through F. So are you okay with that? So I think you all have learned all of this in the lecture. So this is true for any of it. So for a convex mirror, the problem is, so here we get a ray parallel to the principal axis, but the focal point is inside the mirror. So what happens is, the ray will be reflected. It appears to be coming from the focal point. So if you extend the reflected ray, it looks like it's coming from the focal point. Okay, so both of them follow this rule, right? Okay, so first rule is done. Let's quickly go to the second one. Second one is exact opposite of the previous one. So any ray which is going through the focal point will reflect back parallel to the principal axis. So this ray is cutting through the focal point, so it reflects parallel to the principal axis. So same thing happens for a convex mirror. If this ray comes as if it is going through the focal point, it will reflect back parallel to the principal axis. Okay. Okay. So last one, easy one. So any ray which goes through the center, C point, will reflect back along the same path. The reason is C is the center, right? It is the center of the curvature. It's like the radius. So this line is perpendicular to your surface of the mirror. So anything which goes along this path will reflect back along the same path. So it is even true for the convex one. So anything which appears to be going through C will come back along the same path. So are you okay with these three rules? Yes? Okay. So now I want you to draw ray diagrams for these two scenarios. And this arrow here represents your object. And whenever you are starting to draw ray diagrams, you are interested in the image of this object, right? So you have to start drawing your rays from here, the top point of your object. Okay, that is very important. So start drawing all the rays from the top point of your object. So draw all three images, all three rays for the first one, and tell me if you are done. I will start it. So for the first one, I drew one ray. Do you agree with that ray? Do you think it's correct? Yes, right? So the first rule is any ray which goes parallel to the principal axis, that means a ray parallel to this line, will go through the focal point. So that is my first ray. So I think I mistakenly drew the third rule first. Okay, this is the third rule. Any ray which goes through your C point through the center will come back along the same path, right? So usually having two rays is enough to figure out the image. So image is formed where these reflected lines, so this is very important, reflected. So you are interested in reflected. What did I write? Reflect. I wrote something else. Okay. Reflected. Where the reflected lines intersect. So this is a reflected line, right? This is a reflected line. This is a reflected line. So this is the point they intersect, right? So that is where your image is. So we drew rays for this A point. That means the top part of your arrow will be here, like this. So I have drawn the other ray also. I will draw it. So this is the second rule. Second rule is any ray which goes through the focal point will be parallel to the principal axis. So this is another reflected ray, right? So this is a reflected ray. This is a reflected ray. This is a reflected ray. So can you see all the three reflected rays pass through one point, intersect at one point. So that will be the place of your image. Okay. So since we drew the diagram for the point A, what you get is the location of point A, and we know it's the arrowhead. So what can you tell about this image? So I want to tell me the characteristics of your image. So first one, it's upside down, right? See, your image is upside down. So it is an inverted image. What else can you tell? This is your image. So I got another one, real image. So it is correct. Let's see why. What else? Small, it is smaller, right? Yeah. So it is smaller. So you can look at the arrows and compare. So this arrow is bigger than this arrow. Your image is smaller. And how do we know it's real? So if your reflected rays, so these are actual rays, right? These rays actually intersected at this point. So if the reflected rays converge at one point or intersect at one point for real, then it is a real image. Okay, so this point, at this point it really intersected. Okay, so now let's look at the other one. So I'm going to draw the three lines. So my first line, I'm going to draw a line which goes through, goes parallel to the principal axis, and it will go through F, right? Okay. So is it correct? So I kind of extended the reflected line here. This is my reflected ray. So you can see it kind of goes through F. Okay. So my second line, something which goes through the focal point will be parallel to the principal axis. This is parallel to this line. So if I extend my reflected ray, this is my extended reflected ray. So this line, okay, this one, the top one in green. So if I write, so this is the first rule, this is the second rule. The third rule is anything which goes through C will come through C. So same path. So this is, if I reflect it, it follows the same path, right? So if you look at this, can you see at this point right here, no, let's forget about that. So if we look at the actual rays, do they intersect at any point? This one, and this one. So these are the reflected rays, right? This one, and this one. So in front of the mirror, they do not intersect, right? You can see that they are diverging in every direction. So they do not intersect in front of the mirror. So what we do is we look at the extended rays. So we are only interested in the reflected rays. So we look at the extended rays, and we can see at this point right here, these three reflected lines intersect. That means, sorry, your image is here. So this is the point A, right? The top part of your arrow. So what can you tell about this image? This is the image. It is upright. Yes, it is in the same direction as the initial arrow. It is small. What else? Is it real or virtual? So if you can get it right, then you understand what real and virtual is. So it is, you all are correct, it is virtual. Why? The reason is these reflected rays did not intersect for real, right? They did not really go behind the mirror. We just extended them because it looks like they intersected here. So they really did not intersect, right? Because can light rays travel behind the mirror? No. So if you ever see an image forming behind the mirror, then it is virtual, because light rays do not go inside the mirror, right? It reflects off from the surface. So these are dotted lines. These are dotted lines because we just extended the lines. They are not actual light rays. We just extended them because it looks like it came behind the mirror. Okay, so anything behind the mirror is virtual. That is what happened in the plane mirror, right? Even in the plane mirror, the image was virtual because it was behind the mirror. Because light rays do not go behind the mirror. It really doesn't go behind it. So are you okay with it? Okay. So it is the same thing I have put here. Okay. So knowing how to draw those ray diagrams are useful, but knowing how to use the equations are more useful than that. So we are now going to look at how to do whatever we did before. That means figuring out the location of the image, the characteristics of image, whether it's inverted, upright, virtual, those stuff using equations. So what we are going to do is use equations to do that. Okay, so the sign convention. Sign convention means how we are going to use signs. That means plus or minus when we are going to use these equations. Okay, before going to sign convention, we have to know what each of these terms are. So D naught means the distance to the object. So I will call it object distance. It makes sense, right? O stands for object, D is for distance. Di is what? Image distance. F is the focal point or the focus. The distance to the focal point or the focal length. Some people call it the focal length. Okay. So what F is this length. Okay. So all these distances are the distance from the point P or from the lens. Okay. So if you have a object here, this distance from P point to your object is D naught. Okay. If you have a image here, then this distance from your P to the object will be Di. So you get it, right? So these distances are from the P point. Okay. So the sign convention. So F D naught Di, all of them will be positive. All of them will be positive if they are in front of the mirror. In front means this side, right? So for this mirror, for this one, this place is in front of the mirror. For this one, this place is in front of the mirror, right? So towards the left side of your mirror is positive. Then F D naught and Di will be negative if they are behind the mirror. So I want you to look at this carefully and tell me the sign of F for a concave mirror and the sign of F for a convex mirror. So check where your F is, whether it is behind the mirror or in front of the mirror? So I got one correct answer. So do you agree with it? So yeah, good. So for a concave mirror, F is in front, right? It is in front of the mirror. So it is positive F. For a convex mirror, it is behind the mirror. Therefore, it is a negative F. So this is very important. So you should know which one is negative and which one is positive. Sometimes they will give you the value of F. They will tell you F is a negative value and then they can ask you what is it, whether it's a concave or a convex. Okay. So if you know this, you can do anything. So, but there are some nice things that you can figure out from these. So if your DI is what? Image distance, right? If DI is a positive value, that means where is your image? Okay. If DI is positive, that means it is in front of the mirror, right? That means it is a real image. So you can figure out whether an image is real or virtual by looking at the distance. If it is a positive value, that means it is in front of the mirror and it means it's a real image. If your DI is negative, that means it is behind the mirror. That means it is a virtual image. Okay. So looking at the sign of your DI, image distance, you can tell whether it's a real image or a virtual image. Good, right? This is useful. So there's another equation you have to know, that is called the magnification. So this M is the magnification. So using this, you can tell whether your image is bigger or smaller. So how do you do it? This is the height of your image. The height of your arrow. Remember the arrow. Okay. This is the height of your arrow, height of your image divided by height of your object. How tall your image is, how tall your object is. So you divide the two to get the magnification. And they are saying that it is equal to negative di over d naught. Di is the image distance over d naught, object distance. With this equation is also extremely useful. You have to know. So they will probably give it in the differentiate, but it is very useful. So using this equation also you can get lot of information. If your M, if the magnification is a positive value, if it is positive, that means your image is an upright image. So if you want, you can take a screenshot of this slide. It is very important, okay? If your M magnification is a negative value, that means your image is an inverted image. It's upside down. Okay, so looking at the sign of your magnification, you can say whether it's upright or inverted. So other thing is, if you look at the magnitude is without the sign. If you just look at the value, if your value is a higher value than 1, if the magnitude is higher than 1, that means your image is larger. You have a bigger image. It is magnified, right? If it's higher than 1. If it's smaller than 1, that means your image is smaller than the object. So are you okay with this slide? So this is very important. If you want, you can take a screenshot. Okay. So this is something that I got from your lecture. Okay, this is a slide that I copied, screenshotted from a lecture. So for a concave mirror. Okay, so for a concave mirror, you remember in a concave mirror, what was your F? Concave is like a cave, right? So F is positive. F is positive. The images can be real or inverted. So these two things come together. So someone has asked me a question in the chat also. Usually real images are inverted and virtual images are upright. Okay, so these two things come together usually. So they can be either real and inverted or virtual and upright. Okay, so for a concave, that means you can get a real image or a virtual image. If you are going to get a real, it will be inverted. If you are going to get a virtual, it will be upright. Just like the two examples we did, right? If you look at the two examples, real was inverted, virtual was upright. But it was, we only did one example for the concave. So for concave, you can get any of these, any of the two scenarios. But for a convex mirror, this is very important because they can test this in conceptual problems. For a convex mirror, images are always, see, always virtual and always upright. Okay? They are always virtual and always upright. That means your DI is always negative. For a convex, DI is always negative and M is always positive, right? Okay. Then they say as the object distance decreases, the virtual image increases in size and it is always smaller than the object. So always is another always thing. Always the always the image is smaller than the object. That means your M is always less than 1, right? So make sure you go through these things in the lecture. Those summaries are very useful. Okay. So I'm going to the first 3 problems. So I want you to quickly, as soon as possible, do this and tell me the answers. So I got lot of correct answers for the first one. I will do the first one till you do the second one. Okay. So concave mirror. Concave mirror means F is positive, right? You might not need this. I'm just going to write all of this. With a radius 20. So they have given the value of radius. And we know the focal length is half of the radius, right? Remember? So focal length is 10 centimeters. Creates a real image 30 centimeters from the mirror. What does it mean? Real means DI is positive, right? That means it is in front of the mirror. So your DI is positive 30. That is what it means. You remember that, right? From the previous, so if I quickly go to the previous one. Oops. Here I have written DI is positive, it is in front of the mirror. And also if DI is positive, that means it is a real image. Okay. So we know everything what we need. They're asking for the object distance. So if I write the equation, so the answers that you have given for part B and the second one and third one are also correct. So I will continue doing this. So we need this, right? Object distance. Object distance. So object distance is given by 1 over f minus 1 over di. So if you remember how to solve this stuff from parallel resistors, remember this? We can keep it as it is and take the inverse, right? That is how we used to solve parallel resistors, equivalent resistance. Okay. So D naught is given by, what is 1 over F? 1 over 10 minus 1 over 30 inverse. So I have got the answer 15 centimeters. So your answers are correct. B. So the next one. An object is 12 centimeters in front of a concave mirror. In front means object distance is plus 12. So usually objects are in front of the mirror, right? So even if they do not tell this, we know usually you have to stand in front of the mirror to see something. Okay. So concave mirror, F is positive, and the image is 3 centimeters in front of the mirror. So image is also in front of the mirror. So it is also positive, it is 3 centimeters. So they are asking for the focal length, right? So from this equation, we can write F is 1 over di plus 1 over d naught inverse. One over 3 plus 1 over 12. So when you do this, you should get plus 2.4 centimeters. So we get a positive value, right? We know for a concave mirror, F should be positive. For this, like all the answers are also positive, but for my quiz, I might like give positive and negative values, both. Okay. So you all have to know for this mirror, it is positive. For this mirror, it is negative. Okay. Last problem. Not the last one. Last problem in this slide. An object is 5.7 centimeters from a concave mirror. Okay. So usually, like I said before, objects are in front of the mirror. So I'll just write D naught is 5.7. The image is 4 centimeters tall. So they are talking about height, right? HI is 4.7. And also they have given DI is 10 centimeters from the mirror. They're asking how tall is your object? So we can use this equation, right? HI over H naught is equal to negative DI over D naught. So since they are just asking for the height, even if you did not consider this negative sign, it is okay. You can just take the magnitudes. Because this negative sign here the sign of this will represent whether it is inverted or not. Okay, we don't really care about the sign because they haven't said anything about the sign of these, right? So I'll just take the magnitude. So HI is 4.7, H naught is what we need to find. DI is 10 centimeters. DO is 5.7 centimeters. So HO is 4.7 divided by 10 multiplied by 5.7. Am I correct? Yes. So for this we get the answer 2.679 centimeters. So your answer is 2.7 D. Okay, so in this problem they haven't said us anything about this object, whether it's a negative distance or a positive distance. So that is why I just took the magnitude, because they don't care about the sign. Okay. So there are 3 problems here. Let's try to do it soon. So once you are done with one by one, give me the answers. The first one. So once you are done with the other 2, send me the answers. So now it is a convex mirror. For a convex mirror, F is a negative value. So they are saying convex mirror has a focal length of negative 20. So they have given it with the correct sign, right? So let's say they did not give you the sign here. You should know it is negative because it is a convex mirror. Okay. So even if they did not give you this sign, you should know it is negative because it is a convex mirror. So F is negative 20. An object is placed 30 centimeters in front of the mirror. So D naught is positive 30. They're asking for DI. So 1 over F is equal to 1 over D naught plus 1 over DI. So your DI is 1 over F minus 1 over D naught inverse. F is negative 20 and D naught is also, it is positive 30, right? 30. So negative 1 over 20 minus minus 1 over 30. So when you plug this in the calculator and get the inverse, you should get negative 12 centimeters. That means, what does this negative sign represent? It is a virtual image or it is behind the mirror, right? So the answer you should get is 12 centimeters behind the mirror. So it is not here, right? They have given 12 centimeters but in front of the mirror, but it is wrong. So your answer is D. So for the next one, you all have given me the answer as C. So it is correct. Okay, it is correct. C is the answer. So let's see. Object is 14 centimeters in front of a convex mirror. If is negative. In front means DO is positive 14 centimeters. Image is 5.8 behind the mirror. Behind means negative. 5.8. So even if they did not tell you this, you should know. Why? We know for a convex mirror, image is always virtual, right? Remember summary? So usually they give this because they don't want you to know everything, but it's good to know. So they're asking what is the focal length. So when we find focal length, we should get a negative value. Let's see. F is 1 over d naught plus 1 over di inverse. D naught is 14. Di is negative, so I put the negative here. So when we do this, we get negative 9.9 centimeters. So we get a negative value. So if you get a positive value, that means you have gone wrong somewhere. Okay, so negative 9.9. So for the third one, you all have given me answer A. Let's see. So yes, I also got answer A. It is a tricky one. Let's see. An object is 8.9 centimeters tall. So H naught is 8.9 centimeters. The image is 7.8 centimeters tall. And 14.8 centimeters from a convex mirror. So it is convex. So very important. So your DI is 14.8. And what can you tell about the sign of DI? They haven't said it, right? But you all know about convex mirrors. In convex mirrors, images are always virtual. That means it is always behind the mirror, right? Although they haven't said it specifically, you all know that it is a negative value. So D naught, we need D naught to find the rest. Okay. So we can use the magnification equation. We can just use the magnification equation to find D naught, right? So we can just use it without signs, because even with signs we will get the correct answer, but even if we use it without signs, it is fine. So magnification is what? Hi divided by H naught is DI divided by D naught, right? You have a negative sign here. So even if you have the negative sign and use it as it is, still you get the answer. Or by complicate things, we can just take the magnitudes. So what do we get? 7.8 divided by 8.9. Those are the heights. DI is 14.8. I'm just putting the value and D naught. So from this, I get the value of D naught as 14.8 times 8.9 divided by 7.8. So I got 16.88. We know mirror objects are always positive, right? Because you have to stand in front of the mirror to get an image. Okay, so that is why I didn't really care about any signs, because I know it is always positive. Okay, now we have to find the focal length. What is the equation? 1 over di plus 1 over d naught, and you take the inverse. So right here we have to be careful with this sign, because we know it is a convex mirror, therefore di is negative. Negative 1 over 14.8 plus d naught is 16.88. So when I take the inverse, I get negative 120. So this is a hard problem. It is not really hard, but we use the fact that convex mirrors produce virtual images. They haven't given us that this is a negative value, but we used our knowledge to write that it's a negative one. Okay. Okay, so let's do the last one. I will do the last one. Okay. So this is a short problem. So a shaving or a makeup mirror is designated to magnify your face by a factor of 1.4 when your face is placed 20 centimeters in front of it. So M is what? M is 1.4. They have just given us the factor, right? So they have just given us this. And they have given D naught is positive 20. So can you just look at, without even doing it, can you tell what type of a mirror it is? What should it be? So can you see this is greater than 1.4? That means it has magnified your face, right? It is giving a bigger image. If you remember, convex mirrors only gave small image, right? So this should be concave. But let's see. Okay, so I assume that this should be concave. Let's do the problem and see. Okay. So also we know shaving mirrors produces upright images, right? If we think about it, it's not going to turn your face upside down. So that means this is a positive 1.4 upright. So that is why I removed this magnitude symbol, because we know shaving mirror should give you a upright image. So M is 1.4, and also we know M is given by negative di over d naught. So since I know the value of this, whether it's positive or negative correctly, I'm going to use it as it is. I'm not going to put any magnitude signs. So from this we can get the value of d naught. Di. Di is 1.4 times d naught minus, right? We have to take this minus to the other side. So what do we get? 1.4 times 20. So I got negative 28 centimeters. So we have the value of di. Now what we can do is we can apply the mirror equation to find out the focal length. So if our focal length was positive, it is a concave mirror. If it is negative, then it is a convex mirror. So that is what we are going to do. So F is inverse this is negative 28, this is 20. So when you do this, you get positive 70 centimeters. So a positive focal length. It is a concave, right? So our guess was right. So it is a concave mirror. So you all have to know what sort of a mirror is positive and what is negative. Okay, part A is done. Part B, describe the type of image that it makes of your face. So how would you describe it? So we know how to describe it, right? So M was a positive value, right? It was 1.4 because we know it, your face should be upright. It is positive. That means M is a positive value. That means upright. And also M is greater than 1, right? That means it is bigger. It's a magnified image. So it's a large image, larger than the object. What else can you say? DI, you can look at DI. DI was negative, right? DI was a negative value. That means it's a virtual image. So these are the things that we learned in that summary slide. So those are the things that we can tell, right? Okay. Part C. Calculate the required radius of curvature of the mirror. So they are asking for R. So what is R? 2 times F, right? Remember F was half of the radius. So 2 times 70 is 140 centimeters.